Hi, I'm Elena and I'm a PhD student at NICEF in Amsterdam, but I'm actually working on LHCb. LHCb is one of the 4 big experiments at CERN and is dedicated to the search of new physics, looking at B and D mesons decays. So here you can see a scheme of the LHCb detector with all the subdetectors. In particular, the one I'm working on is the VELO, the vertex locator, which is about this size, and it is the closest part of the detector to the proton-proton collision point. Here on the screen you can see how a typical event looks like in LHCb. So you see all the tracks going through the subdetectors, and if we now zoom on the VELO part, we can distinguish many different vertices. These are all proton-proton collision points, and this is the purpose of the VELO, so reconstruct the vertices. This allows us also to see an important feature of the B decays. So the B mesons fly a distance of about 1 centimeter before the decay. And if we look at the transverse plane, we can see this, because here there is the primary vertex, and then we have other 2 tracks in here which converge at this point, which is separated with respect to the previous one. This point is the secondary vertex where the B meson decay. So this is why the VELO is so important. Now, in 2018, we are going to perform an upgrade of our detector, because we want to improve our precision on the measurements, and in order to do that we need more B decays, and since we are limited by our hardware trigger, we want a triggerless readout at 40 MHz. So what does it mean if you look at this picture? This means that after the upgrade, in this picture there is going to be 5 times more tracks. So as you can see, this is a big challenge, because that means that we have to upgrade all our subdetectors, and in particular for the VELO, this means that we have to cope with an increased data rate and with high fluence. But at the same time, we want also to maintain our high resolution and our excellent vertex reconstruction. So among the many changes we are going to apply at the VELO, we are also going closer to the beam, so at a distance of 5.1 millimeters, and we are going to replace strip sensors with pixel sensors. So here there is a picture of the VELO, of the upgraded VELO. So you see the 2 alpha and the modules, and each module look like this. So we have 2 sensor tiles on the front part and 2 sensor tiles on the back part. A sensor tile is this one. So as you can see, is really small, is 3 times 14 mm, about 14 millimeters wide, and the pixel size is 55 by 55 micrometers. So what I'm actually doing is I'm characterizing these sensors. So we have a wide range of sensors. We have both N-on-P and N-on-N sensors. They have different thickness, and they have also different gathering size. So what we do, we test the sensor and then we analyze the data. So how do we test the sensor? We have our beautiful telescope, which is this one. It consists of 4 sensor planes on one side and 4 sensor planes on the other side. These provide the track reconstruction and timestamp that we can compare to the response of our sensor, which is placed here in the middle. So we send the beam through our sensors, and then we look at what we see. Here we see the beam on the sensor planes, in here and in here. Instead here, this is our sensor, the one I showed you before, and the beam on our sensor. So this is what I'm doing, and as you can see, it's really challenging, but at the same time it's great fun.